and hopefully maybe even have a little bit of a demo. So here's Stephen White, PhD, computer scientist, lead developer, and I know everybody has been waiting on the edge of their seats for this talk, so I'm very excited.
Good afternoon. So Austin gave us an excellent introduction into the talk, and I think I've broken down the talk into some of the components of the BioGears API that I think everybody should be familiar with when they're integrating to get the optimal performance. We're going to start with a basic example of the architecture like we talked about yesterday, and then our dimensional analysis components where we store our scalar values and common interfaces in the API. And then I'm going to go through a couple of how-to examples that explain how to do basic integration components into BioGears when you want to run it in conjunction with another platform. So to start out, again, the BioGears API is divided into 3 major layers. And for modern integrators working in the 7.0 line, if at all possible, they should stick to the synthetic environment layer, which represents all of our abstract interfaces for common physiology descriptions, and the BioGears engine layer, which is our concrete implementation of the BioGears human physiology model. There's a third layer, which is in our API layer, that's our serialization component, and there are certain things in the synthetic environment that require you to reference classes from the CDM, but when possible, for future proofing and integration in BioGears, you should keep your code that uses anything in the CDM : namespace or fully expanded milled Tatric physiology data model to a minimum. So the first major thing that anybody who's interacting with BioGears does outside of standing up an instance of a physiology engine is to try to get data back from BioGears on what's going on with the virtual patient. And as soon as you do that, you're going to begin interacting with a large section of the synthetic environment layer called the SE scalar and SE unit scalar interface. SE unit scalar extends SE scalar. In between them in the inheritance chain is a template called SE scalar quantity, which nobody should have to work with directly, and mostly is a way to simplify our code when implementing new scalar models, and it helps us in our logging code. Each one of these unit scalars represents a different combination of fundamental scientific units and the ability to automatically convert between equivalent representations of that unit. And we have about 54 different scalar combinations from, length, area, volume, to length per time, velocity, speed, going on into more complex concepts like concentration and molality. The common interface for any of these types is the set and get value functions, which when you set a value, you hand it the current double representation that you want to set it to, and then you hand it a unit representation that number is expressed in. If the underlying model for the scalar is different than what you've expressed the set in, we will auto-convert it to what the underlying model is and store it for you. And then when you call get value to get that value again, you can express any one of the supported conversion units, and it will automatically convert to that scale and return to you the equivalent value within double point precision. As it exists, there are operators for all of these scalar types that allow you to add similar units to each other automatically without using these functionalities or subtract. But we currently don't support multiplication and division to do auto-conversion to higher levels or lower levels of dimensional analysis, which is something that we're looking to expand in the future. The thing that I want everyone to take away from this talk is that the cost of getting any of these pointers to your heart rate, blood pressure, or a compartment data request is very expensive because it uses a lot of string comparison. But the pointer that you get back from any of these get scalar calls, or if you drill down through the Physiolgy API to get a specific scalar, is good for the lifetime of a physiology engine or a current patient load state. As long as you do not load an entire new state and you just advance time, or you destroy the physiology engine, you can continue to call get value on the same pointer at every time you advance time, and you'll get the updated internal representation of what that value is. And this is a much more optimized way to keep a data cache of the pointers that you're interested in your integration and to continually get their update just by polling their current get value each cycle that you advance the BioGears model time. Next thing I want to talk about is the synthetic environment is mostly composed of two large abstract interfaces. One is the SE system, which represents all of the representations of our internal organ structures and compartments, and the other is the SE action, which represents any insult, injury, or intervention that you can do to a patient. We have a couple of more specific derived types from that, but when we interact with them, they are all upclassed to the SE action. So your patient actions, your environment actions, your anesthesia machine actions, they all extend from the same common interface. And if we were ever to add a new action category, it would also extend from this interface of how to properly retrieve data to it, how to serialize it, and determine what version it is when we're marshaling and unmarshaling data. And systems follow that same way. If you ever wanted to expand the resolution of BioGears, you would start with a base SE system and then extend from there, eventually making a concrete class in the BioGears engine layer. So this is the smallest example that I can come up with for integrating with BioGears. And the takeaway here is that BioGears consists of two data libraries, libBioGears and libBioGears-CDM. libBioGears-CDM is where we store all of our exported serialization data, and BioGears is where all of the SE interface and the BioGears interface live. And so to do anything with BioGears, you have to link against both. And then depending on how you're integrating, you might also need to hard link against our two external dependencies, Xerxes-C and log for CPP. So that gives you a total of 4 linker calls that need to be made. The project currently uses the C++ 14 standard, but we are looking to upgrade our compiler requirements and to start using C++ 17 features, notably the file system header to improve our abstract file system handling. So this represents the average compile flag you would use on an Apple or Linux or Unix system. And then for compiling on Windows, CMake automatically generates you a Visual Studios project, which is available to the community for free through the Visual Studio Community Edition. And so you don't have to worry about any of these compile time flags, but it is good to know like what you would need to do to set one up if you were extending. The main example that's presented is just a simple example of instantiating the BioGears object, which starts with creating a logger, passing that logger to the create BioGears engine function, and then loading a state or a patient. So in this example, I take a serialized patient that comes with the BioGears base system and load it in. If that doesn't return an error, I advance the model time by 1 hour. And BioGears tends to run at a rate of about 6 to 1 simulated seconds to wall clock seconds. So you're looking at about 10 minutes or so for that hour to pass before it's done. So in a normal integration, you would do much smaller advanced time steps so that you could check and do work in between them and still stay real-time and interactive with the patient. So for anybody who's integrating with BioGears a lot, the first step that I always start with is to wrap our own creation function with that boilerplate code from the first example. If I'm going to fall back from a load state to a custom patient, or if I don't have a custom patient, I'm going to fall back to an existing patient file, I go ahead and stick all of that conditional lattice work inside of the create function and make that the first thing that I write. and then I return by moving the unique pointer to a BioGears engine to whoever calls that function, and that creates the ownership model going forward that this is the only copy of the physiology engine I'll be using in this thread. Now, the BioGears library is inherently single-threaded for a single simulation, but you're allowed to run parallel as many copies of different physiology engines that you want that could be doing alternative timelines or multiple patients. And we think this is the best utilization of the way that people want to use BioGears, because when you're integrating with it, you don't want BioGears to consume your entire system just so that it runs a couple of milliseconds faster. It's better that we keep the single-threaded model running faster than real time so that you have all the rest of your machine to handle your integration events or to be able to spread parallel computation at the same time. So this comes to a question. The examples up to this point have examples of standing up a BioGears engine pointer. But our create physiology engine function returns a unique pointer to a physiology engine pointer. Physiology engine is the synthetic environment most abstract reference of what BioGears can be. And all of its function accessors are consts, and everything that they return is consts. And the idea for the physiology interface is that once you've advanced time, you're not going to modify any of the components of a simulation anymore. So that's why they return constant. You're just going to get data and let the simulation run forward or apply actions and interventions that are safe that will modify the underpinning data on the next advanced time. That is great for running how-tos or running scenarios, and it's the interface you should use. But if you're integrating a full front end where you might allow people to manipulate the environment in the middle of a run, or you might need to go beyond what is already available, the interface, as long as you apply to a certain amount of safe rules that are best to use, is the BioGears engine class, which is the concrete implementation class of the physiology engine in BioGears. And that allows you to access non-const members of the actual concrete implementation, access the renal physiology engine instead of the synthetic environments layer. And you'll just find more power from integration there instead of constantly casting between physiology engine and BioGears engine when you need to kind of break the interface limitations that physiology engine imposes. Okay, so more meat into, we're going to go into a couple of examples. Most of the examples for the early part of this talk come from an example included in the BioGears code base called How-To Integration. And this is just an example of how I segregate my code so that it's easy to maintain when I'm writing any of the UIs or utilities that we've run. So this is a short example of how to apply a hemorrhage action in BioGears. I create a function that returns a Boolean, and it is passed to BioGears engine pointer by reference. The ownership model that I assume here is that nobody will be advancing time on the pointer for the physiology engine that is passed to me while I execute this function. And in multi-threaded examples, I often assume that this function will run in the same thread as advanced time is called to guarantee that. If those two assumptions aren't correct, you need to guarantee that you write critical sections around advanced time and your calls to apply action or anytime you manipulate the code manager, because internally we assume those are single-threaded occurrences and they can't happen at the same time. So this begins with setting up an SE hemorrhage action. There are no concrete versions of any of our BioGears actions or insults. Setting the individual components that we're going to apply. You could add these as parameters to the applied pain stimulus. This is a static reference of the type of hemorrhage that could be applied. Then calling is valid to verify that you have set all of the required components so that it is a legal action to pass into BioGears. And upon that being true, call process action and pass that hemorrhage. That hemorrhage will be deserialized. It will be unmarshaled and remarshaled to create a declone on our side. So you're free to destroy the memory of the hemorrhage that you passed into BioGears after calling process action. And you could repeat this for all of the actions in BioGears and just equivalently change the function signature to match the parameters that you're willing to change inside of your process action. And it'll give you a clean demarcation of where any of this occurs in code. So the reason for a lot of this methodology and kind of strict coding is that currently all BioGears classes that extend from the SE layer lack copy constructors. And so they don't have a safe way to clone memory allocation. There's a lot of times in our API when you pass us a pointer that we assume we now get to destroy it. And the Doxygen comments inside of our code base while we are improving this thoroughly denote when this happens. So it's often an integrator problem that they accidentally create memory with something that's managed by like a garbage collection allocator. It gets passed into BioGears, it runs for several minutes, garbage collection destroys that, and then all of a sudden BioGears crashes 5 minutes after you actually initialize the problem. So the bulk of this talk lies in how to safeguard your way around this and when to focus on making sure that things stay lifetime. And so I'm demonstrating that internally for all of our process actions, process assessments, we work around this through cloning through serialization. But that does have a performance cost in the terms that we take the binary representation you pass to us, we convert it to text, and then we immediately reinflate that back into binary so that we have a clone and you're good to go on with the data. There's a point at the bottom of this slide where I call delete. And the thing that I want to communicate here is that if you manually call any of our unload functions, we call new inside that unload function. And we do not clean up the memory that we hand you back. You take ownership of it. The problem is that we don't expose deletion functions inside of our DLL bounds. So you'll be deleting that memory on your side of the DLL, and depending on your specific architecture, that could be inherently unstable. So deserializing your own objects from SE classes can be an unstable component of our API that we're working to resolve in the serialization refactor. So with that in mind, I do encourage everybody integrating with BioGears to prefer composition over inheritance. So BioGears is very object-oriented. It uses a really deep inheritance model, as we've already discussed, for abstract interface classes. Some of them are 3 and 4 layers deep. But once you get to the other side of the DLL bounds, we actually also expose a lot of STL templates as data members currently in our headers. And so if your definition on your side of the DLL for basic string is slightly larger than the definition of exactly what was compiled in BioGears, when you inherit from any of our objects that have a string in its member, your definition of how large that class is will be different. And so casting operations on your inherited children will fail because the memory mass of where our BioGears starts compared to where you believed it started will be wrong. And it causes a lot of instability when integrating on Windows platforms with Widecard or UTF-8 enabled platforms with BioGears, which is inherently ASCII based. So instead of doing that, keep all of our pointers as members and replicate our interfaces, even though it takes a little bit more time, and you will be infinitely more memory safe and run into less problems when working in BioGears. In the future, we look to alleviate some of these problems, and this will become safe, but it will take us a while because these are API breaking changes that create binary incompatibilities, and so a lot of discussion has to happen before it can be resolved. So in that note, to repeat from the beginning of the thing, once you have done by composition, it is safe to create member pointers to any of the data points that you're going to be calling often for updates. So you look back to our visualization talk that we gave yesterday, we keep several patient metrics on the screen at all times, I go ahead and keep those as a cache every time I do a state load. And then anytime I advance model time, I just call get value on the pointers that I keep, and I place the results of those in a double buffer that goes to the UI. So I have two places of memory space allocation, and the get scalar call is much faster than continuing to call, well, the get value call is much faster than continuing to call get scalar and going through the large amount of conditional checks that happen to pull out the specific scalar you requested. This can be the difference between like milliseconds and microseconds in performance, and you will definitely see more fidelity in your application if you use this cache methodology. So this is an example of what the data request cache could look like. So allocate the members inside your own class that you're going to keep permanently. At the beginning or every time that you call load state or you create a new physiology engine, assign these based off of whether they exist. Every data request in BioGears has a has function, which will tell you whether it's been initialized or already there, and a get function. In the non-const version of the get function that returns a star or a pointer to an SE scalar of the type returned, we will auto-inflate it if it hasn't been there. But if you're loading from state, then everything should already be inflated. The has function will validate all of that, and you can return null pointers instead of getting a pointer to a nan-initialized member, because that'll communicate that that value is never going to get used inside of the simulation, because whatever configuration you have in your patient in BioGears didn't need them during initialization, so they probably won't be needed going forward. Then every time you advance model, I go ahead and create a struct that's going to act as my buffer for the actual double values that I'm going to expose to my integration. And I keep a function which refreshes that by just calling get value on everything that isn't a null pointer. To fit in these slides, I'm heavily abusing the ternary operator, so it may be a little confusing. But you basically have the member of my current buffer assigned to whether or not my member function is a null pointer. If it's valid, I get the value, else I return 0 or some control value, sometimes -1 or nan. And that allows me in my UI to test for special visualizations when these values aren't present. So from there, the other thing I wanted to cover today is patient assessment. So these work very much like applying action, but you're getting data out. So you have to provide BioGears memory of a specific SE assessment, in this case, the urinalysis. And then you call from the physiology interface, get patient assessment. It will automatically populate all of the data members for you, and then on return, you just check to see if there's a result for everything you're interested in, and decide your way to expose that to your interface. Because I don't like using any of the CDM types, here, while I'm processing the urinalysis, I go ahead and open switch for anything that returns in the urinalysis of a CDM enum, and I convert it. So this example is very simple. It just does direct output to FCD out, but you can also convert here to an integer or a duplicate enum for yourself. And the thought process here is, instead of having 4 files that know what an enum urine color is that may be deprecated in the next year or two, I have one spot in my code that knows what an enum urine color is, and I just have to change that one function to our internal replacement that will be in the BioGears namespace, and everything will continue with minimal refactoring effort on an integrator side. So just about containment for future pending changes. So the rest of this presentation focuses on asynchronous development. I think this is probably going to be the #1 way that anybody uses BioGears. You have something that needs to be interactable to take interrupts from a user interface, whether those be momentary buttons, mouse clicks, or keyboards. And at the same time, it needs to respond to data to BioGears, which is always running probably throttled down to real time. And so we need to start a thread which owns a BioGears engine. We need to advance time in a way that keeps up with wall clock time. And then we need to be able to pass the events that happen in the user thread for pressing that I'd like to apply a hemorrhage, or I'd like to run a urine analysis, or please get me the respiratory rate, to that thread, call all of that data, and execute it, and then return the result. And how to do that safely and simply so this isn't a large burden on the end user. We have a couple of examples in the code base. There is a how-to multi-threaded BioGears. The how-to integration that I mentioned earlier is also a multi-threaded example. It runs through a static scenario, but with very little effort, you could imagine expanding that to be a dynamic scenario. And we will soon be exposing an Unreal 4 engine plugin that supports BioGears. That is a more detailed explanation of how to do this, along with our visualization code, which does it in Qt. So you have two large widget platform reference examples that are publicly available. And because both of them were coded by the core team, they use similar techniques, but then adapt to that platform-specific requirements. So for example, everything in BioGears is kept in double precision, but Unreal is a floating point only engine so that it's optimized for the video card. And then the interfaces that we sometimes have to expose are actually in half precision. So they're only in 16-bit floating points. And so we have to make sure that everything we get out of BioGears is automatically safely casted and in units where it'll be in a range that's visible and not just clamped to 0. So with that in mind, this is the engine main thread for the BioGears class for Unreal. It does a couple of things. Once it is called and stood up as a thread, it checks to make sure that BioGears should continue to run. That's the variable engine thread continue. And then it checks to see if the engine is paused. If the engine is not paused, then it tries to pop off a queue of work, which we'll go into in a second, and advance time by 1 second, and then broadcast all of the metric updates that happened over that time. So every time you advance BioGears time, it's internal state changes. And so if you want, whether you need to expose 1 metric or 200 metrics, they have all become new. And so the greatest concern to an integrator is at what refresh rate you actually want to pull all those updates, whether it's every time you advance or every few times, and that is left to the integrator to decide. But this broadcast method is an Unreal version of a signal and slot, which will send a Boolean notification up to the code that's listening to it that these double buffers have been updated and that it's now safe to grab all their values and refresh them to the user. The other thing at the bottom that you'll see is the throttling code. Basically, I sleep in 16 millisecond intervals to check and see if it's been longer than 1 second since the last time I advanced by a second, and that's how I clamp BioGears runtime down to real time at a rate of roughly 60 hertz a second to check in that. So you get pretty good fidelity on it actually being 100% real time. So some boilerplate code into this. These are examples of starting an engine thread. All of this code is based off of the C++ 14 like standard thread implementation. So we start a thread, we pass this that engine main. That is a class member pointer, so it has to get a pointer to the instance of BioGears engine driver. And then I like to add broadcast mechanisms to my UI that all of this happens, just to tell it that it started. Pause and resume, very similar. I have an atomic Boolean engine pause, which my main thread checks the value of. When you call pause resume, I set that state in an atomic variable, so there is a critical control built into the engine underscore pause type. I don't have to write my own mutexes for that to work. And then for stop, I manipulate all of my control variables into a safe shutdown state, broadcast that they've changed, and allows that thread to go one more advanced time tick before it shuts down, to make sure that there are no asynchronous problems before the thread's called unjoin. Anytime we're working with threading, it is a runtime exception to delete a standard thread without having called join on it. It's also a runtime exception to call join if join has already been called. So, and that doesn't mean that multiple threads can't call join, but the joinable flag has to be high. So there's a PSA to everybody. Always, if joinable on your thread, then call join, and you'll have less surprise hit when something goes wrong or is too fast. And finally, this is just a really simple way to set the throttle. I keep that as an int, so I can have multiple steps of real time versus max time. And I broadcast what rate something was set to in case there's like 2 or 3 UI threads or some asynchronous thing going that needs to be communicated to multiple parts of the UI. So earlier I said, and I can go back to it real quick, the second while loop in this example, which is about 7 lines down, says while action queue has a size, and then in this example it doesn't pop the time, but in the real version of the code, it immediately consumes a member of that when it's valuable. What that is a thread-safe channel, something that allows multiple sources to push work in and only one consumer. And it takes in lambda pointers to avoid star. So I've created in my driver class several wrappers for all of the applications that my UE4 plugin supports using that apply hemorrhage example we had earlier. This one is for applying tourniquets. And then the driver class, when those are called, it takes the same parameters, but it just wraps the function call that will be deferred to until it's consumed from that thread into a lambda that's inserted into that queue, so that when we consume it, we can immediately call that using the function notation of just an extra set of parentheses. It will execute the internal sides with those copied in variables, so we don't have to worry about lifetime. And you'll get this code executed inside of the main thread, but deferred from when they were actually requested in the UI thread. So the question becomes, how do we get information back? Well, if it's an action, it's just instantly applied. You could create a signal in slot here that's going to execute to say, this signal went high and we did something, but most likely what you actually want is to wait for a patient assessment, which would be deferred by the same method, and then to expose that as a double buffer up to the UI that can get pulled every frame. So once they see that the data's changed, they just display it. It becomes kind of like a promise system from the asynchronous side of standard thread. So everything that we just went through, we have public examples on GitHub for the Qt5 under the visualizer. And we will have, if it's not already uploaded as of today, the Unreal Engine 4 code, which is a plugin that can be popped into any instance of Unreal, and then with a little bit of work integrated into your game, and will run BioGears through a scenario that you're having and allow you to apply different actions and insults that we are currently supporting in the thread. We're looking to maintain both as just a way to expand support for BioGears. We have projects which are funded that currently need these technologies, and we think it's good for community outreach just to make them available, and that is our model. Couple of things to note that we've gone over, and I might have gone over too quick. If you integrate with these large projects, they normally have type requirements or inheritance things so that they can be exposed safely into their system. Like when you work with Qt, everything needs to derive from Qt objects. And when you work with Unreal, there is a U class and a U object class that everything has to derive from, so it inherits all of the common functionality of the platform. to get BioGears working out of the box with the CDM for that, you would either have to modify the XSD patient generation so that your version was incompatible with standard BioGears, which I denote is not the best thing to do, or inherit a class that does multi-inheritance from a Q object and a BioGears object. This will work fine, and we have integration examples where it happens. This is where the pointer arithmetic I warned about earlier comes into being a fault, that when you start trying to look at things as just the BioGears side of that multi-inheritance triangle, you might get arithmetic errors that cause rogue pointer behavior at odd times. It might take you drilling down to 2 functions and then casting the return of that before you see it, but it inherently creates some instability that we're working out. But for now, I suggest taking the third approach, which is just to always do everything through composition. Go ahead, copy and paste our enums as they exist and recreate them on your side in a single enum header. Create translation functions, which when we return those enums, you get to buffer them into your typeset space and can be exposed to your platform. And when passing into these complex applied actions, just go ahead and create structs that are just the members that you would want to support out of that action, and you pass that as a single input to your function signature, which also makes it easier for you to maintain these apply functions because they just take in your struct, you go back to your struct header, you add the extra things or remove them that you want to support, and you have less things to maintain because everything's common across your integration platform. I think it makes life easier, and it makes our life a little bit safer when we start approaching these refactors that we're looking forward over the next 12 to 24 months. So this would be an example of the platform adapters. These are just 2 of the CD enums. If you were not going to support all of our exercise states, or you wanted to have support for more based off of a combination of metrics, you would add them here and do the translation. Your UI interface would always use your enum, so even if we change our mapping, you just have to change the mapping layer where you do the conversion to keep up. And most of this is very stable in BioGears, and it doesn't change that often, but if we change our serialization input, it could change a lot of code for you if we don't keep it in one place. But that's the goal there. And this would be an example of a class adapter where we just take that urine analysis and we keep an unreal state version that's all floats instead of double returns. And then every time we assign this, we go ahead and do the clamp checks with casting and range. And it's a time where you could document the exact metrics that you want to expose to your UI. So any of these that were scalar units, you could add to the name the specific scalar unit that you're going to combine and maybe not what BioGears keeps internally by default. So that is the bulk of the talk. I'm open for any discussions, and I'm available through the GitHub interface. We also just opened up a dev developer for Slack, and we'll hopefully be able to make signups to that public if anybody needs one-on-one help in the future.
Awesome. Thank you, Stephen. That was really great. And again, a lot of these examples can be found by just cloning our libraries right now. And then some of them will be supported and pushed up onto GitHub in the next few weeks. So stay tuned. If you're signed up on the Sketch website that I've been posting in the chat, I have the ability to send out emails to everybody who's signed up. That is the list I'm going to be using to send out an update about the PowerPoint availability on GitHub. So please, it's still useful, even though we're almost wrapped up here, to still sign up so that when I send those bulk emails, you get the information that you want. I'll also send a link to our YouTube page that we'll be posting the full spoken presentation of each of these talks. So does anybody have any quick questions before we move on to our last and final talk? Otherwise, as always, feel free to reach out